Alright, hello everyone. I hope you guys are doing good. So today I'll be discussing the solutions to Codeforces Round 763. So as you can see, the round is still going on, but apparently I have lost all hope of solving the fourth problem. So I thought, why not make a solution video? So I will be discussing the first three problems in this video, A, B and C. And before starting, if we talk about the round, it was all in all a good round. The difficulty level increased gradually, and it was one of those traditional 5 problem Div-2 rounds, in which the fourth and the fifth problems are generally really hard, as is the case in this round. And as far as the first three problems are concerned, the first problem is really easy. But starting from the second problem, you need to make some observations. And for the third problem, again, you need to know some tricks and you need to have them in your inventory if you need to solve them, right? So this was the analysis for the round, and all in all a good round. I don't have any complaints here. So let's start with the solution to problem A. This is going to be a short video with just 3 problems. Oh, first of all, I'll just remove this dark mode. Right. So this is a pretty involved problem statement, but essentially what it says is that we have a robot which is initially at a cell RB, CB in an n cross m grid, and there is one dirty cell RD, CD. And what happens is every second the robot moves in some direction, right? So there is a value dr and dc, and in every second the row of the robot changes to rb plus dr and the column changes to cb plus dc. Initially dr and dc are 1, and as and when the robot hits a final row or the final column, for example, if the robot hits the row number n, then dc changes its value from 1 to -1. That is, in a way, the robot is getting reflected. Similarly, if the robot reaches the last column, that is, it reaches column equals to m, then dr turns from 1 to -1, and after that, if it again reaches the first column, then dr turns from -1 to 1. So it keeps happening like this, and the robot is kind of getting reflected, which is shown very nicely in this cute animation here. So yeah, that's what the scenario is. And essentially we just have to find out what is the time after which the robot will be able to clean the dirty cell. And what happens is, once the robot is at a coordinate r, c, it cleans all the cells in the rth row and the cth column. So essentially we need to find out what is the time at which the row of the robot or the column of the robot will coincide with the row or column of the dirty cell. That's what we have to find out. If you look at the constraints here, the constraints are really small. N and M are up to just 100. So what that means is that in at most 100 operations, we will surely be able to clean our cell, right? So what that means is we can just in a straightforward way simulate the process. And we know that in at most 100 operations, we will get to our required answer. So we can just simulate the process, and as and when we hit the row of the dirty cell or the column of the dirty cell, we will be able to say that we have found our answer, right? And we will just break out. So yeah, we basically in a way have to simulate the entire process. And to make things more clear, let's just have a look at the code. Yeah, so here it is. I have taken all the inputs and I'm maintaining my position of the robot in RB, CB. So if RB equals to RD or CB equals to CD, that just means that I have reached my desired location. So I will just break out of the loop. Otherwise, I need to make some changes. Otherwise, I'll check whether I need to make any changes to dr or dc or not, first of all. So if dr is equals to 1, that is my robot wants to go right. My robot wants to go down, and it is already on the last row, then it can't go down. So dr will become -1. Similarly, if it wants to go up, but it is at the first row, it can't go up. So dr will become 1. And I have done a pretty similar case analysis for the column as well. So I have fixed my dr and dc values, and what I'm doing is I'm just incrementing my rb by dr and cb by dc. And I'm also incrementing my answer because we need to find out the minimum time. And all of this is happening in 1 second. So I will do answer plus, and finally, well, I will reach my dirty cell. Then I will just break out. I will reach a cell which shares either a row or a column with the dirty cell. I will break out, and I will have the correct answer with me, right? So yeah, this basically completes the solution to problem A. Let's move on and discuss problem B. It required some observations, although the observations were not very difficult to make. As you can see, a lot of people have solved this problem. Around 6.5 thousand people have solved it. So yeah, it's kind of not that difficult, right? Okay, so let's see what this problem says. So we have a set S of disjoint ranges. And initially this set only contains one range, that is 1 to n. And what happens is, in each operation we pick a number from any range within our set, right? So basically what happens is, first of all we pick a range from our set, and within that range we pick a number d. So for example, we picked the range L comma R, and from that range we picked a number d, and then we will remove L comma R from our set. And what we'll do is, we will essentially break this range down into two parts after removing d. So if I remove d, then the range will be broken down into two parts, that is from L to d minus 1 and d plus 1 to R, right? Obviously there is a corner case when d is just equal to L. In this case we will just be left with one range, which is from L plus 1 to R. But ignoring that for now, we'll be left with two ranges. First is from L to d minus 1, and second is from d plus 1 to R, right? So these are the two ranges that we'll be left with. So every time we will do this. So in each operation we are decreasing the size of the union of all the ranges by 1, right? Initially the union of all ranges is 1 to n, and the size is 1, and the size is n. It has all the elements from 1 to n, and in each operation we are removing one element from this union, right? So that means in exactly n operations we will be left with nothing. So that is what's going on. And after playing the game, what happens is that we remember all the ranges that we picked, but we don't remember any of the numbers that we picked, right? So we remember all the L comma R values, but we don't remember the D values. So essentially we have been provided with all the L comma R values, and we have to assign a D to all of these values, right? Yeah, so this basically is the problem. The constraints are small, although it doesn't matter. The complexity of the solution is around O of n only, or maybe if you implement it lazily like I did, then it can be O of n square as well. So let's see what's going on. Yeah, so it is probably a good idea if I try to explain these sample tests here. So if you look at this sample test 2, what's going on is, initially n is equals to 3. So initially we will just have one range, which is from 1 to 3. So basically we picked this range, and once we pick this range, we will pick a d value, and that will break our range into two more ranges, right? So as you can see here, the two ranges that are left with us are 2 comma 3 and 2 comma 2. But 1 comma 3 is breaking down into two ranges. That can only and we are getting 2 comma 3 after that. That can only happen if we choose d is equals to 1, because once we choose d is equals to 1, we'll be left with this range 2 comma 3. Right? So for the range 1 comma 3, we are choosing d equals to 1. Then we are left with this range 2 comma 3. And as we can see, after removing 2 comma 3, we are getting this range 2 comma 2. So that is only possible when we pick d is equals to 3 for the range 2 comma 3. So for 2 comma 3, we will pick 3, and then we'll be left with 2 comma 2, for which we will pick a 2. Right? So yeah, this is the sample test case explained. So I hope the problem is clear enough now. Right. So this is the problem, and let's see how we can do this. So problem B. So what's happening is, we are starting with a range 1 comma 1. So we are starting with the range 1 comma n, I'm sorry. And in each step choosing a range, right? So we are essentially choosing a range and breaking it down into two parts, right? That's what we are doing. Also, there is this corner case where we are just when we are taking d is equals to L, in which case we are just breaking this range down into one part. But I think we can ignore this. We can just take care of that separately. So yeah, that's what is happening. So let's see from the beginning. So initially we have 1 comma n, right? So we have 1 comma n. So once we choose a d for this range, we will be left with two ranges, which are 1 comma d minus 1 and d plus 1 comma n, right? But the main observation here is that out of all the ranges starting from 1, the range which will have the maximum value of r will be this range only, 1 comma d minus 1, right? That's for sure. So the observation here is out of all ranges starting from 1, the one with the maximum r will be this particular range 1 to d minus 1, right? So there is that. But another corner case here is that if there is no range starting from 1, in that case we can be sure that the d value which we chose for this range 1 comma n is equal to 1, because that is the only case where we will have no range starting from 1, right? So if we have no range starting from 1, and obviously I am assuming that I am not considering the range 1 comma n itself, so I am considering all the ranges other than 1 comma n. So if we have no range starting from 1, then d for the range 1 comma n is just equal to 1, and this is the main observation, and using this we can solve this problem. But this is just solved for the range 1 comma n. What about the other ranges, right? So what happens is that once we have solved for 1 comma n, we can just solve this problem recursively. So what I'm trying to say is that once we are here and we have figured out this range from 1 to d minus 1, what we can do is that we can recursively solve this problem for 1 comma d minus 1 and also solve this problem for d plus 1 comma n, because we will be sure that these two ranges will surely be present. So we can recursively solve for these two ranges. Similarly, in this case, we know that if d is equals to 1 was chosen for the range 1 comma n, we will be having a range 2 comma n here. So we can just solve recursively for 2 comma n and let this process continue. And once we solve everything recursively, we will get to the right answer for sure, right? So that's it. This completes the solution to this problem. Let's have a look at the code for better clarity now. Yeah. So what I'm doing is initially I am keeping a vector of answers which will store the answer for each range, and also I am keeping a set of pairs ranges where I will store all the current ranges that I have, right? Okay, so I take in all the ranges and I insert them into my set. So what I'm doing is I'm erasing the range which I'm currently solving on. So I'm currently solving on the range 1 comma n. So I will erase that range because I have already mentioned that I'm looking at all the ranges other than the current range, right? And then I will call solve of 1 comma n. So in the solve function, what's going on is that I will try to find out, so I have solve of L comma R. So as I already explained, I will try to find out the range which is starting from L and has the maximum value of R, right? So I'm iterating on my set of ranges. So if I find out that the ranges dot first is equal to L and the ranges dot second is greater than my previously found value of R, then I'm updating my previously found value of R. So by doing this, I am making sure that I am finding out the maximum value of R for any range which starts at L. So yeah, so the first case is that I don't found any range starting with L. In this case, I know that the answer for the range L comma R is just L. So I will push that into my answer vector. And then I know that I will find the range L plus 1 comma R in my set. This check is basically unnecessary because I know that I will always find it. Or yeah, this check comes in handy when the size of the range is just 1. So if I have a range 1 comma 1, then this check comes in handy. Because then if I don't have this check, this recursion will keep happening infinitely and I will get a stack overflow error. So I'm checking if I have this range L plus 1 comma R in my set or not. If I have it, I am erasing it and I am calling for solve of L plus 1 comma R, right? Okay, now the second case is that I find a range with the maximum value of R. So I know that the answer, the found maximum value of R would be d minus 1. As you can see here, I am finding the range d minus 1. And so the answer would be found R plus 1, right? So I push that into my answer vector L comma R found R plus 1. And then what I do is I erase this range L comma found R, right? Because now I have to solve for this range. And then I check whether I have this range found R plus 2 comma R or not. So found R plus 2 is nothing but d plus 1 comma n, right? So I check whether I have this range found R plus 2 comma R or not. So if I have it, I also erase it. And then I call solve for both of these two ranges which I got, that is found R plus 2 comma R and L to found R, right? So yeah, this is how the recursion works. I know there might be easier implementations or easier approaches to this problem, but during the pressure of the contest, this is what I could think of. And so this is what I am discussing here, right? So yeah, this completes the solution to problem B. Let's now move on to the next problem and the last problem that we'll be discussing today, which is problem C. So looks like the contest is over, so it makes sense to check our rank. Okay, this system testing is going on, right? All right, let's see. So yeah, now problem C. A lot of you might be interested in problem C. Around 2011 people are able to solve it. Okay, So yeah, so the according to this problem, there are n heaps of stone, and the ith heap has hi stones, and we want to change the number of stones in the heap by performing the following process exactly once. So what we'll do is we'll iterate all the heaps starting from the third heap to the last heap. We have already been given that n is greater than equals to 3, so it's not going to be a problem. So we start from the third heap, and let's say we are currently at the ith heap. So what we do is we choose the number d such that 3 into d is less than equals to the number of stones in my heap. That is 3 into d is less than equals to hi. And then what I do is I move d stones from the ith heap to the I minus 1th heap, and 2d stones from the ith heap to the I minus 2th heap. So in a sense, what is happening is my hi is becoming hi minus 3d, my hi minus 1 is becoming hi minus 1 plus d, and my hi minus 2 is becoming hi minus 2 plus 2d. Right, in one operation that's happening, and I'm doing this for all I from 3 to n. I'm free to choose this number d according to my liking. So I can choose any amount of d provided it fits in these constraints, right? And I need to tell what is the maximum number of stones in the smallest heap after this process ends. So essentially, I have to tell what is the maximum value of the minimum value of hi. So this becomes a maxi-min problem, a mini-max or a maxi-min kind of problem, right? Yeah, so I hope the problem statement is clear enough. It makes sense to explain one of the examples. Yeah, so we have this first test case 1 to 10, 100. According to the problem, the answer to this test case is 7. And we can achieve this answer by doing something like this. So we start from the third stone and we move 3 stones and 6 stones to the third and the second heap respectively. That means we are choosing d is equals to 3. And so the array will become something like this: 7, 5, 100. 10 has become 10 minus 3d. 2 has become 2 plus d, and 1 has become 1 plus 2d. After that, I am moving 6 stones and 12 stones from the fourth heap to the third and second heap respectively. That is, I am choosing d is equals to 6 here. So 100 is becoming 100 minus 6d, which is 82. 100 minus 3d, which is 82. And the 1 is becoming 1 plus 6, which is 7. And 5 is becoming 5 plus 12, which is 17. And I can see that the minimum value here is 7. And it turns out that this is the maximum minimum value that I can get. Right. So yeah, this is the problem statement explained. Finally, we need to tell what is the maximum value of the minimum value that we can get. So let's start with the solution. Well, according to the problem statement, we need to find the maximum value of the minimum value. And what do we think about when we hear this, minimax or maximin? Well, whenever we hear something like this, the first thing that we should try every time should be binary search. It is a very, very standard thing that whenever you hear something like the maximum value of the minimum element or the minimum value of the maximum element, it is always kind of plausible to use binary search, and it just makes sense to first of all think about binary search. And in this problem, it turns out that binary search works. Binary search will give you a full score. Binary search will be applicable here. Well, how to actually ascertain whether binary search will be applicable or not? Try to check whether you can find a checker function or not. Try to check whether you can make a checker function or not. What is a checker function? A checker function is basically you set a value for your answer and you check whether that particular value is possible or not, right? So I am doing binary search for answer. So I will set an answer and I will try to check whether that answer is possible or not. And if it is, if you can write such a checker function, then voila, binary search can successfully be applied to this problem. And as it turns out, in this problem, binary search can be applied since there exists a valid checker function. So binary search for answer. Answer is the minimum value, right? Minimum value of any pile. Out of all these minimum values, the answer is the maximum value, but it is the minimum value in any pile, right? So I will fix a minimum value in the pile, and I will check whether it is possible or not to get an arrangement such that I am doing all the operations, and the minimum value is greater than equals to the minimum value that I have set, right? So I need to find check of x, which returns true if it is possible to do all operations such that after all operations h of I is greater than or equals to x for all x. If I can write such a checker function, then I can easily apply binary search for answer here. So let's see how we can write check of x. So in check of x, we need to make sure some things, right? And what do we have to make sure? So we need to make sure that after taking stones from the ith pile and after adding stones to the ith pile from I plus 1th and I plus 2th pile, the final value of h of I is greater than or equals to x for all I, right? I need to find whether it is possible to have such an arrangement or not, such that once we take 3D stones from the ith pile and then we add some stones from the I plus 1th pile to the ith pile, then we add some stones from the I plus 2th pile to the ith pile, the final value of h of I that we will get should be greater than or equals to x for all I, right? So that's what is happening. But what we see here is that it's not a very natural thing. We don't know how to do it, right? We can decrease any amount from h of I and we can add any amount to h of I. So it doesn't make any sense and it looks like binary search is going to fail. But with this one observation, it becomes really easy. And that observation is that if we iterate from the reverse order, then we will know exactly how much we are adding to the ith pile. Why is that so? And that's because for the last pile, we know we are not adding anything to it, right? So we are sure that we are not adding anything to the last pile. And another thing that we know is that we know the initial value of the last pile, and we know that we need h of n to be greater than or equals to x, right? So we need h of n, that is the final value of h of n, to be greater than or equals to x. And that means that the maximum value that we can subtract from h of n is nothing but h of n minus x, right? So we can subtract h of n minus x because we just need to keep it greater than or equals to x and nothing else. So it makes sense to decrease h of n as much as possible, right? So why not just decrease it? Why not just convert it to x, right? Yeah, so that's one thing. So this way, this is the main observation here, that we are starting in reverse order going from n to 1, because in that way we know how much we are subtracting from every number, and so we can keep track of how much we are adding to the previous numbers, right? Okay, so now we know how much we are adding. So we know that we can maintain an array add of I which stores the number which we are adding to the ith pile. So it can store the number of stones we are adding to the ith pile. So what I'm trying to do here is that I have h of n, right? So the maximum number of stones that I can take from h of n is h of n minus x, and the number of stones that I will take will be equal to 3d. So the maximum value of d that I can get is nothing but h of n minus x upon 3, right? And I can distribute this value in the ratio 2:1 in the n minus 2th and n minus 1th pile. So in this way, I have successfully calculated the add value of n minus 2 and n minus 1. So yeah, this is what I'm doing. This is how I am maintaining this add of I vector. So using this array, I can keep track of the number of stones that I'm adding. So now when I'm at the ith stone, I need to make sure two things. So we need to make sure two things. The first thing is that since if you notice in the question, we are allowed to do the operations from left to right. So what that means is that when we will take the stones from the ith pile, we will take it from the original value of its height. So let's say the original value is original h of I. So we need to make sure that if we take 3d amount of stones from the pile I, we need to make sure that 3 into d is less than equals to original h of I, right? So that's the first thing that we need to make sure. And the second thing that we need to make sure is that the final value of h of I should be greater than or equals to x, right? So final value after adding elements from the I plus 1th and I plus 2th pile. So final value of h of I should be greater than or equals to x. But what is this final value? This final value is nothing but initial value of h of I minus 3d plus add of I, right? And d can be easily calculated as original value. So d can be easily calculated using this using these two observations, right? So what we need to satisfy here is that first condition is that 3d is less than equals to original I, and the second condition is that the final value should be greater than or equals to x, that is h of I minus 3d plus add of I should be greater than or equals to x. So using these two values, I can figure out what d I have to use, and these are the only two conditions that I need to satisfy, right? So I can actually figure out what the d will be that I will be using, and I can assign a final value to all my array elements from 1 to n. And at the end of all this assignment, I have successfully assigned the final values to everything. So I will just iterate from 1 to n and check whether the final value of the heights is greater than or equals to x or not for every pile or not. If it is smaller than x for any pile, then I will just return false. Otherwise, I will return true. So in this way, I have my checker function ready with me. Now I can successfully apply binary search here. So let's just have a look at the code of the binary search. Right. So yeah, I'm taking in the array as input, and I know that the minimum element itself will remain if I take d is equals to 0 for all the operations. So I know that the answer will be greater than or equals to the minimum element, and hence I am initializing L by the minimum element and R by some very large number. And then I apply binary search. I do mid is equals to L plus R by 2, and I create this array final value and this array add. So I am iterating from n to 3. I am going only till 3 because I am not allowed to do any operations for 1 and 2. So I am going for n to 3, and I know that I know the value that I have to add to the ith element. It is already stored in add of I. So if a of I plus add of I minus mid is less than 0, then obviously I can't make it mid, right? So OK will be false, and I will just break out of this loop. So if that's not the case, I have to satisfy two conditions, right? D has to be less than equals to h original h by 3, and d has to be less than equals to hi plus add of I minus x by 3, right? So that's what is happening here. I'm taking the minimum of h of I by 3 and h of I plus add of I minus mid by 3, right? This is the way you will calculate d, such that both these two conditions are satisfied, this condition and this condition, right? So I have successfully found out d. So I will do final value of I as h of I minus 3d plus add of I, and I will increment add of I minus 1 by d and add of I minus 2 by 2d. And once I have done everything, I also have to assign final values to the elements at index 2 and 1. So final value of 2 will just be a of 2 plus add of 2, and final value of 1 will just be a of 1 plus add of 1. And I will just iterate over the array. I have already made sure for all the elements from 3 to n that their final value is greater than equals to mid, but I had to do it for 1 to 2. But anyways, I'm just going over the entire array and checking if their final value is greater than or equals to mid or not. If that's not the case, I am doing OK equals to false. Finally, if OK equals to true, I'm assigning L to mid. Otherwise, I'm assigning R to mid. That's just a standard invariant binary search. The invariant here is that L is always possible, right? And R is never possible. So finally, I will just output L because I am keeping this invariant that L is always possible. So L will be the maximum possible value which is possible, and that is what I need to find. And yeah, outputting L will give me the correct answer. So this is all for this video. Thank you for watching till the end, and I'll see you in the next one. Bye bye.